Hello, today we're going to be talking about conjugate diameters of an ellipse. And our goal here is to prove that with any ellipse, the sum of the squares of any two conjugate diameters is equal to the sum of the squares of its two axes. So what does that mean? Well, the first thing to figure out what that means is we need to understand what a conjugate diameter is. The most simple definition is that two diameters are conjugate if and only if the tangent line to the ellipse at an endpoint of one diameter is parallel to the other diameter. So let's visualize that. I'm going to scroll down here to a diagram, and let's look closely at this. So if we look here, we've got an ellipse, and we've got two conjugate diameters. One is dk, the other is pg, and then we've got two axes. We've got bl and ae. And so this conjugate diameter pg, if you were to take the tangent line, I'm going to draw the little vector here that'll be kind of like the tangent line. You draw the tangent line to the ellipse at point P. If it's a conjugate diameter, then it's going to be parallel to dk at that tangent line. And in the same way, if we were to take the tangent line at point D here, if we were to draw that, it's going to be parallel to line PG. And that's going to make that a conjugate diameter. And what we find out about these conjugate diameters is that if you take a diameter on an ellipse and then you rotate it, say we rotate it in this direction. So we're going to rotate, let's rotate PG in this counterclockwise direction, a quarter turn of a circle, then we're going to end up with this line dk. So this line PG is the same as dk, just rotated the quarter of a circle, and that's a conjugate diameter. And we're going to use that little fact to prove what we want to prove here. And what we're trying to prove is that if we take the square of the length of dk and add it to the square of the length of pg, it will be equal to the length of bl squared plus ae squared. So that's a bit of a mouthful, but let's start at the top and go ahead and prove this out. So the first thing I like to do when I'm trying to prove something is get a really good diagram to visualize it. So, and especially when you're writing a program to diagram something, you're going to learn a lot about that function. So where do we start? Well, we know that the equation of an ellipse is x squared over a squared plus y squared over b squared equals 1. And the easiest way in Python a lot of times to get something plotted is to parameterize the curve. So how do we parameterize a curve that is an ellipse? Well, the easiest way to think is to think about it as a circle. So let's start there. How do we parameterize a circle? You might remember from the unit circle that the way that's done is for the x component, you take cosine of t, and for the y component, you take the sine of t. But why is that? Can we visualize that? Let's try to visualize that really quickly. So here's the unit circle. A unit circle is basically a circle plotted with a radius of 1. So what we're saying is that this distance from here, basically from the origin to some point on the circle, is always going to have a length of 1. And then you've got the x component. If we wanted to plot that point up there, we'd have our x component, and then we'd have our y component. And if we take that x component and that y component and our hypotenuse here, we've got a right triangle, and we can use the Pythagorean theorem to evaluate that. But we also have these trigonometric functions, right? Remember what the cosine is. The cosine is the length of the adjacent over the hypotenuse. Well, the hypotenuse here is 1. So the length of the adjacent is just the cosine. And then the length of this length here, which is our y component, that is the opposite over the hypotenuse, and the hypotenuse is 1. So that's sine. So if we want to parameterize this curve, as we're going around this curve, we're following all these points, making all these little right triangles. Basically, what we're just saying is we have the cosine of t for x and the sine of t for y. And that should draw us a circle. As t increases around this at 2 pi, as t goes from 0 to 2 pi, then all these little right triangles are going to form, and the x and y coordinates are going to draw this circle. So let's see if that works. We have our vector value function here that we have parameterized. Like we said, it's just cosine t and sine t. Then we lambdify it, and then we plot it, set the axes to equal, and make sure the grid shows, and we plot it, and sure enough, it draws a circle like we expected it would. And so now, what is an ellipse? Well, an ellipse is just, a circle is an ellipse. A circle is an ellipse that is not stretched at all. But if we were to grab a circle and stretch it out sideways by a factor of 2, we'd have an ellipse, right? And that's what these little a and b components up here are. And these little a and b components on our equation for ellipse, that's basically saying how much we want to stretch it out. So it turns out if we were to parameterize our ellipse, we have these multipliers here, a and b, In this case, we chose 2 and 1. So what we're saying here is that let's take the x component and stretch it out by 2 units. And the y component, let's not stretch that. We're just going to multiply that by an implied 1 there. And so sure enough, you can see as we plotted this, that the x component here is stretched out by a factor of 2 on each side. And so our parameterized curve basically becomes this a times cosine t for the x component, and the y component is b times the sine of t. So let's go ahead and prove this out. We've got our labeled diagram up there, which we went through and explained. And what we're trying to do is we're trying to say that this length PG squared plus this length DK squared is equal to these axes AE squared plus BL squared. And we've got our parameterized ellipse curve. And so we should be set here. So first thing we want to do is we want to get the distance from C to P. Well, just like we did with the unit circle, we can recognize that CP here really is going to create a right triangle. So we've got our x component and our y component of this right triangle. So CP is the hypotenuse. And so CP is going to equal x squared plus y squared. So what is x squared plus y squared? Well, we take our parameterized curve values and we plug them in there. And we've got an equation for CP, which is the x component squared plus the y component squared, and the square root of that by the Pythagorean theorem gives us CP. And so if we wanted to get this entire length, the entire length from P all the way to G, we know this is all symmetric, so all we got to do is actually just multiply that by 2. So this gives us our next important piece of information here, which specifically is that PG is equal to 2 times the square root of a squared cosine squared t plus b squared sine squared t. Now, moving on, this is where it gets a little more tricky. We need to figure that out for this line dk. So let's start with half of dk, which is CD. What's going to be the length of CD? Well, it's our same, we can use our same parameterized values here, but the value of of t at this point here is going to, from the difference from point P to point D. Remember we said we were rotating those a quarter circle, so we're rotating it pi over 2. So what do? We add pi over 2 to each of our t components here in order to get this point. So CD is going to be, remember, we've got this little leg of our right triangle here. If we're trying to get CD, so we're going to say the distance of this leg squared plus this leg squared, we take the square root of that, then we're going to get this hypotenuse, which is CD. So we did that down here. We just took that parameter, t plus pi over 2, which is going to give us that point that we're concerned about, that point D, and then we plug that into our parameterized curve and use the Pythagorean theorem just like before, and we got the length of CD. But now we want to get the full length of dk. So the full length of dk is going to be from here all the way to here. Well, that's just 2 times the length of dc. So we just multiply that by 2. That's exactly what we did here. We multiplied the length of CD times 2, and we got dk. So there's our formula for dk. Okay, so now we've got 2 very important things for our proof. We've got the length of PG, and we've got the length of dk. And they look almost similar. And if you've messed around with trigonometric identities a lot, anytime you start to see cosine squared plus sine squared, you start to get tempted to try to put it into a shape where you could say sine squared t plus cosine squared t equals 1, right? Because that's one of the things that comes out of our unit circle, is that sine squared t plus cosine squared t equals 1. It's a well-known trigonometric identity, and if you can factor that out, then you can get rid of these trigonometric components on your equation. So a lot of times when you're doing a proof like this, that's where you're trying to go. So keep that in mind. If we can get things factored out such that cosine squared t plus sine squared t is together and multiplied, and we can turn that into 1 and maybe get rid of those. So how do we do that? Well, it's hard to do right now because of these little buggers right here. We had to add this pi over 2. And so we're kind of comparing apples to oranges here because we've got 2 different t components. So what can we do with that? What can we do about that? Well, let's think a little bit about what cosine and sine are. I went ahead and graphed cosine and sine on this pie plot here. And You might notice something important here. Cosine and sine are actually the same exact wave shape. They're identical. It's just that they're offset by a little bit. How much are they offset by? Well, we said earlier that these conjugate diameters are offset by pi over 2, and it's a pretty good guess that sine and cosine are also offset by pi over 2, and sure enough they are. So cosine t plus pi over 2 is actually equal to negative sine t, and sine t plus pi over 2 is actually equal to cosine t. So this is this. I'm going to go ahead and highlight that for a moment. Sit and think about this for a minute. This is an important thing to remember, that you can convert back and forth like this by putting this offset here in the parameter. And I illustrated that a little further down here, where I said, okay, let's go ahead and plot both of these. In the parameter, I'm just going to put that pi over 2 offset there and see what happens. And sure enough, I plot it out, and the lines are right on top of each other, and you can't tell the difference between them. So how does that help us? Well, it helps us because we can just substitute in using these little formulas here to try to get our parameters to equal each other. And that gives us what we need in order to do the proof we need to do. So using our formula for PG and dk above, remember we have PG squared equals 4a squared cosine squared t plus 4b squared times sine squared t. And then dk squared equals the same thing, just with this offset here on the parameter. But let's go ahead and plug in our sine wave for the cosine wave offset mentioned above here, and translate this. So what was cosine squared? We look up here, we said cosine t plus pi over 2 is equal to sine t. So that means if we were to square that, it's just equal to sine t. So that means down here is that we can take this guy here and turn him into this guy here. And vice versa, we can take this guy here and turn him into this guy here, which is great. Now our parameters are starting to look like each other, and maybe we can factor things out to get that 1. So we have PG squared equals this expression, and dk squared equals this expression. So that's pretty useful. And let's talk about real quick about our axes. So it's pretty clear that ae squared equals 4a squared and bl squared equals 4b squared. But just in case that's not clear to everybody, let's go look at it in the diagram. So what we're saying here is that if we wanted to take this value of this distance here and square it, we know that the distance from C to A is B, and we know that the distance from C to B is 1, and therefore we can figure out that AE squared equals 4A squared, and that BL squared equals 4B squared. So if we want to say AE squared plus BL squared, we've got 4A squared plus 4B squared. Now, let's go ahead and see if we can do the more complicated part of PG squared plus DK squared. So we took our PG, here I'll just erase this for a moment. We took our PG squared and DK squared up here, and we're going to add them together here, and we get this expression here. And then we move things around a little bit, like I said earlier, to try to factor out that cosine squared t plus sine squared t, because that is equal to 1. And we were able to shuffle those around just a little bit in order to factor this out. And we can factor out the cosine squared t plus sine squared t from each of these terms, which is equal to 1. And then it gets us to this expression here, which is PG squared plus DK squared equals 4A squared plus 4B squared. And since we know that AE squared equals 4A and BL squared equals 4B squared, then we've got this expression here, which is PG squared plus DK squared equals 4A squared plus 4B squared, which is equal to AE squared plus BL squared. And what that means is that PG squared plus DK squared equals AE squared plus BL squared, which is exactly what we were trying to prove. So what did we prove there? What does this expression mean? This expression means that the length from PG, we square that and add it to the length DK and square that, that value is going to be the same as BL squared plus AE squared. And that's our proof. Thanks for watching.